Hi, folks. This time we are going to talk a little bit about moment of inertia and we're going to talk about angular momentum. But let's talk originally about moment of inertia. Now, moment of inertia is how the mass is distributed around axis of rotation and how this affects how easy it is to rotate an object or stop the object from rotating. Now, I think one of the most common examples is unrolling TP or paper towels. I'm assuming most of you have seen this somewhere in your life. And if you think back to occasions where you have encountered a full roll of TP and an almost empty roll of TP, think about when is it easier to unroll it? When does it unroll slowly? And when do you pull on it and it unrolls very, very quickly? Well, that's the difference between a high moment of inertia and a low moment of inertia. Now, if you said to yourself, when the paper towel or the TP is very, very full, it unrolls relatively slowly. That is because it has a large moment of inertia, and I is the letter we use in physics for moment of inertia. When it is almost empty, it has a relatively small moment of inertia, and that is a combination of its mass and how far that mass is from the axis of rotation. Lots of different examples of this moment of inertia. Two great examples are diving or gymnastics and dance. So if you look at a diver, if a diver wants to spin or rotate very, very quickly, they will tuck. They will get their body really tucked into a little tight ball and they will spin really fast. When they want to come out of that spin, they untuck and they make their body long. This is going to have a small moment of inertia, meaning a fast rotation, and a big moment of inertia, meaning a very, very slow rate of rotation. Dancers do the same thing. If a dancer wants to rotate quickly, the dancer is going to pull their limbs very close to the center of the axis of rotation, and that is going to allow her to spin very quickly. When she wants to stop rotating, then she is going to put her limbs out, and that's going to give her a large moment of inertia, and it's going to control her rate of spin. Now, there are in the world of physics wonderful equations for moments of inertia, and they depend upon the radius, how far that mass is from the axis of rotation. The mass itself, something with more mass is going to have more inertia. So it's a combination of not just the radius and the mass, it's both together, and then how does that object roll? So if you're talking about something that's shaped like a pencil, is it rolling across the desk or down the desk like this, like rolling off the table? Or are you standing your pencil up on end and twirling it side to side? So the axis of rotation matters. And that's why we use all these different equations if we really want to analyze that moment of inertia. So if you have a situation where you want something to not spin or spin very, very slowly or resist spinning, one of the ways you can do this is take some mass and move it a long way away from the center of rotation. People who are brave enough or wacky enough to be tightrope walkers. I remember as a little kid going to the circus with my family and seeing a tightrope walker, and this person had a long, long, long pole. Now, as a child, I thought the pole was because of the fact that if the tightrope walker got scared, they could lean on the pole and that would be their exit strategy off the rope. But this soul is above Niagara Falls, so that's not going to work. What they're doing with this long pole is it gives them a very large, long moment of inertia. Small change, little microscopic motions with his fingers over here is going to have small changes on this far ends of both ends of the pole, and is going to make him very much more stable. We do the same thing when you and I are walking down a railroad track or walking down a curb. We naturally put our arms out. By putting our arms out, we increase our moment of inertia. We want this big moment of inertia to keep us from spinning. And our spinning is right through that central axis. So we make ourselves wide by putting our arms out, and we resist toppling over. Goalies in hockey, catchers in baseball, they are going to be low and wide. Low is going to give them a low center of gravity. Wide is going to give them a big moment of inertia to make them hard to topple, because you don't want somebody running into home plate or somebody coming into the goal and knocking over your goalie. It's a bad thing. If you have an outrigger on a boat or a catamaran or something like this, you can take a long, skinny boat and you can make it very, very stable, because these outriggers are going to add that extra moment of inertia. Now let's talk about animals or people with very long legs. If you are a human that has very long legs and you have some friends with not so long legs, you probably notice that you swing your legs in a very slow, deliberate manner. Why? Because your legs are long and you have a large moment of inertia. Giraffes, really long legs. Big moment of inertia. They swing and spin slowly. The axis of rotation is way up here in that joint. And they don't spin very quickly, but they don't have to, because they have big amount of distance that's covered with every single stride. Now, to contrast that, if you have an animal like this cute little dachshund, and this little dachshund has small little legs, small moment of inertia. When the dog swings her little legs, little tiny steps, or your dear friends that are not so vertically enhanced as you might be, they have to swing their legs a lot more often and a lot faster because of the fact that they are shorter. This is the great gymnast Simone Biles. And Simone Biles, I found this picture and I went, wow, she is spinning on this axis, and you can see how tightly she is just tucked up. And that is because she's trying to give herself a very small moment of inertia to allow herself to do a really, really tight spin. If you talk about turning radius of a car, if you look online for cars with a really small turning radius, tight turning radius, they are not going to be Cadillacs. These are not going to be F-150 pickup trucks. These are going to be tiny little cars like Fiats. Why? They're going to be small cars with a very, very short front to back distance, because of the fact that you can only have things that with a small moment of inertia if you want them to turn quickly. Now, if you put together this moment of inertia and the rate at which something spins, which we refer to as angular velocity, you can come up with something called angular momentum. We've talked about momentum some in the past, and linear momentum is mass times velocity. Well, angular momentum is how fast something spins times its moment of inertia. And there's a law of conservation called the law of conservation of momentum. Actually, it's a principle. I actually have that incorrect. Principle of conservation of momentum. And it applies to both linear and angular momentum. And it says the momentum before and after the event. And the event is the hit, the explosion, the jump, whatever causes the change. Both of those momentums are going to be the same. So let's look at some examples. Classic example of conservation of angular momentum is an ice skater. As a child, again, I would watch this on TV and was fascinated. How could someone go from having their legs extended, their arms extended, and then they'd tuck really, really, really tight, and they'd be rotating really crazy fast? Wasn't until I studied physics that I understood it was conservation of angular momentum. The momentum, which we use in physics, capital L2 as its symbol, is the same in both situations. But here, she has a very small moment of inertia. Everything is tight. Everything is tucked up close to that axis of rotation. And so she has a very large angular velocity, really, really fast spinner. Here, she's got her limbs far out. She's got a big moment of inertia, and she has a small angular velocity. What's amazing is a person can actually change their rate of rotation just by distributing their mass. You redistribute your mass, you can change your rate of spin. And athletes, dancers, divers, gymnasts do this all the time. And this is one of the things they have to master in order to be fabulous in their field. In the world of mechanics, there is a thing called a mechanical governor. And there's lots of different governors. The old-fashioned ones from over 150 years ago looked more like this, but they were weights attached to springs or arms that would move. And what would happen is as the velocity at which something rotated changed, as the rate of rotation changed, these things would rotate further out and further out. Well, as they came up and rotated out, it would cause some sort of a valve to open or close, depending upon how the whole thing was rigged up. And these can be used, and they are in large and small examples. They are used today in engines and this is an example I found from an airplane. Pilot throws the throttle forward and it can change the little governor on here, the little flyweights will change this spring and it'll change actually the rate of velocity of the propeller. In engines, you've got little weights, and as the rate of fuel flow changes, this will spin faster and slower, and it will open and change a valve. It is a wonderful example of angular momentum and it being used on a fabulous little totally mechanical valve that does not contain a lot of electronic parts. You can calibrate it and set it how you like, and it's been around for almost 200 years, these little mechanical governors, and they are found all over the place. All right, folks, that will conclude this section, and we will see you later. Bye-bye.